And we are back in topic 12, permutations, combinations, and the binomial theorem. Today, we are specifically going to look at permutations. What is a permutation? That's an arrangement where order matters. So you have a whole bunch of objects, you stick them somewhere, but the order you put them in matters. If you have a whole bunch of athletes, 3 of them get to be on a podium, well, it kind of matters who's first and second and third. Order matters. When you change the letters around in a word, you get a new scrambled up word, but each order of those letters is different. So those are called different permutations. Some of the permutations we have will only involve some of the available objects. For example, you have 5 pictures, you want to arrange them on a shelf that can only hold 3. How many ways are there to do this? Well, as we would have done when we used the fundamental counting principle, we would have had a slot. Well, that's a flick pretzel. We would have had a slot for picture number 1. We would have had a slot for picture 2. We would have had a slot for picture 3. And we would have said there are 5 options for the first picture. And then once that's picked, there are 4 options for the second picture. And once that's picked, there are 3 options for the third picture. And by the FCP, we'd be multiplying those all together. This involves a part of countdown multiplication. And we refer to that countdown multiplication with factorials. It looks kind of like 5 factorial. But 5 factorial is 5 times 4 times 3 times 2 times 1. So really, we've taken that and divided by the 2 times 1. We've chopped off these n2. Delete. So there's a way for us to express something like that called permutation notation. If we have 5 objects and we want to pick 3 of them, we would write it as 5p3. What that means is we're going to take 5 factorial and divide it by 5 minus 3 factorial. So in this case, that's what we'd get. We'd have 5 factorial divided by 2 factorial, which is the same as what we said above. So it chops off the latter bit of that countdown multiplication, the last little bit of that factorial, depending on how many objects you want to take. For example, you have 12 friends and acquaintances or tag-alongs, just a group that's walking along. They're not walking along these days because that's too big a group, unless they're in the same household, in which case fine. But they're walking, they encounter some benches. Oh no, the benches can only seat 8 people. So how many ways can they arrange themselves on these benches? Again, you can create the slots and say that you've got 12 and 11 and 10 and 9 and 8. Oh my goodness, that's so tedious. Enough of this. Instead, just say, well, from the 12 people, we're going to pick 8. I know the P is actually for permutation, but I like to use the word pick. You're picking 8. In some order, specifically. Now, calculator-wise, you should have a button that says NPR, like this. So, to put that in your calculator, let me just move some stuff around. It's a good calculator color. This. So on your calculator, you're going to press the 12. You're going to hit that NPR button, and then you're going to hit 8. And that will give you the value. In this case, it gives you the value of this. So we've got nearly like 20 million ways of arranging those people. That's just 12 people. Wow! That's a lot. So initially this is like kind of straightforward. Single scenario, you have some number of objects, you're arranging some number of them. But you could also have constraints and cases, and you're going to have to deal with each one separately. And there are so many ways to approach any of these. And it's honestly pretty easy to get confused, so you will have to be careful. There could be cases that are straight up distinct. If that's the case, you want to look at each of the individual cases and then add a number of possibilities together. For example, if you had a license plate that was only numbers and a license plate that was only letters, those are completely independent. There's no overlap between them. So those would be cases where you could add together. But sometimes there's a case that applies within a larger scenario. And then you're going to have to use the FCP in order to put all that together. And we'll see that applied. In this first example, we meet Winnipeg's top DJ, DJ Noel. Now, he's not the top DJ yet, he's just starting out. His library is extremely small. Whoa! Sorry, I just had a quick power outage. It was like half a second, but it was very exciting. It was a dark and stormy night. Irrelevant! DJ Noel has 8 upbeat songs and 4 slow jams. I don't know if that's the best ratio. I don't personally think he has enough songs in his library, but it's all he can afford right now. That's what he's got. How many 8-song playlists can he make that have exactly 1 slow jam? Well, it means if you want to use slots for this, if you want to use slots like that, you have 8 options for where to put the slow jam. But once you've done that, you have to fill in the other 7 slots with upbeat songs. There's 8 of them. That's more than we need. So from the 8, we need to pick 7 of them. But then we still haven't actually picked which slow jam we're going to use. Boom. In a sense, we're going to pick 1 spot out of 8 to actually place the slow jam. We are going to pick 7 out of the 8 songs, out of the 8 upbeat songs, and we're going to pick 1 slow jam out of the 4. These are all cases within the same scenario. They're all built together. This is multiplication through the FCP. So your whole result is all of those multiplied together. 8P1 being multiplied by 8P7 being multiplied by 4P1. That entire thing has to go into your calculator, and you should get a number like... You're fine, you can't read your own writing. That. In this case, we have the word at least. And there are multiple ways to approach this. So you could say, if it has at least 1 slow jam, then it could have 1 slow jam, or it could have 2 slow jams, or 3 slow jams, or 4 slow jams. And then you can solve each of those cases separately. We've already got how many ways there are to have 1 slow jam. But then you'd have to figure out how many there are that have exactly 2, or exactly 3, or exactly 4. That could be a lot of work. Here's the thing. If it's got at least 1 slow jam, you know what it doesn't have? No slow jams. In this case, when I see this at least 1 business, I'm going to find out how many playlists there are at all. So how many 8-song playlists? Well, he's got 12 songs total. He's going to pick 8 of them. But how many have no slow jams? In that case, he's only going to pick his 8 songs from his 8 upbeat songs. No slow jams? That's all you get. And there's that many arrangements of that. This is how many possible playlists he could make. This is how many playlists don't have any slow jams, which means the rest of them must have at least 1. So total number of playlists, and get rid of all the ones that don't have any slow jams. And we get this. So still quite a few that have at least 1 slow jam. Most of these playlists have at least 1 slow jam. But how many have all 4 slow jams? My goodness. We're going to approach this one just like we did in A. We're going to use all 4 slow jams. So the first slow jam has 8 spots it could fit in. The second slow jam has 7 spots. The third slow jam has 6 spots. And the fourth slow jam has 5 spots. That's when we're taking our 8 tracks and just saying 1 slow jam will go here, 1 will go here, 1 will go here, 1 will go there, wherever you want those slow jams to go. We're deciding where they go. But let's just note that this means that out of 8 possible spots for those slow jams, we are picking 4. Once those are filled, we need to pick we need to pick 4 songs out of the 8 upbeat ones to fill in the rest. And for picking 4 songs out of 8 upbeat ones, that's 8p4. So, if you want all 4 slow jams, we're going to take 8p4, we're going to multiply by 8p4. Yeah, they're both 8p4, but be aware that they come from different sources. So just note why we chose 8 in each case, why we chose 4 in each case. And we get a result. Do, 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 do. Pacha! And that's the app. You'll notice over here, I wasn't really using permutation notation to figure things out. You don't have to use it every single time. Often I will still set up these blank slots for myself so I can really start envisioning what's going on. If you need to do that, that's perfectly fine. Go for it. Do whatever you need to do to find the way forward. Believe in yourselves. Believe in the dream. And believe these next examples are about to happen. Get ready. Ka-chow! Aw, we had a group of 10 friends. That's so nice. So we've got this random group of 10 friends. They have names. They decide to go watch a movie because, everyone's out there watching movies right now. That's the best time. And they have to sit in the same row of 10 seats because, the person on the very left is going to absolutely need to see the person on the very right. It's fine. It's fine. All right. How many ways can they arrange themselves in the row? Whole bunch of ways to approach this. If you want to set up the slots, 5, 6, 7, 8, 9, 10, go for it. And you can say you have 10 options there and 9 options there, 8 options for the third seat, and so on, so forth. And of course, multiplication in between. Or you could say that, looking at that above, that's just 10 factorial. Or you can say that out of 10 people, you're going to pick some order of 10 people. All of these are the same. And all of them will get you this answer. There's that many ways. Oh, but Jimmy absolutely insists on being in the first seat. Okay, well. You have one option for this first seat then. Jimmy's there. And in these other seats, we're going to put everyone else. You have 9 options there, and 8 options there, and 7 options, and 6 options, and 5, and 4, and 3, and 2, and 1. Or you can say that we have 1 times 9 factorial. Or you can say that we have 1 times 9p 9. This is Jimmy, and that's everyone else. However you choose to calculate that, you should get this answer. We're going to look at a whole bunch of cases for these bestest friends. So over here, we're going to have Juliana and Tajel at the very ends. If you want to set up these slots 4, 5, 6, 7, 8, 9, 10. Cool. And at the very ends, so this is Juliana or Tajel, this is Juliana or Tajel. You have 2 options for one end, which then puts the other one at the other end. Cool. And in this middle zone, you have the other 8 people. 8 options for the first, and 7, and 6, and 5, and 4, and 3, and 2, and 1. What we've really got is this many ways to arrange Juliana and Tejal. And you're going to multiply that by the number of ways to arrange everyone else. And you're going to get values. This one, I got that. Oh, this is an interesting one. Jason, Noel, and Alex must sit together. Oh my goodness, they are so needy. Here's what we're going to do. We're going to stick them in a box. There you go, guys. This is your box. But you know what? Everyone gets to be in a box. Person 4 gets to be in a box. And person 5. And person 6. And person 7. And person 8. And person 9. And person 10. There. Everyone gets their own little independent boxes, but over here, Jason, Noel, and Alex can have their box where they can sit together. Within the box, there are 3 factorial ways to arrange them. There are 1, 2, 3, 4, 5, 6, 7, 8 boxes. And Jason, Noel, and Alex don't have to be in these first 3 spots. Their box could move anywhere else. They can be over there in between positions 4 and 5. So there are actually 8 factorial ways to position those boxes. By the FCP, we need to multiply, because for every arrangement of boxes, there are 3 factorial ways to arrange Jason, Noel, and Alex. And here we get that many ways. You can continue trying these. There's a few more to go. See what you can do. These aren't necessarily the easiest, and it is going to require some thinking. Feel free to use whatever strategy you need to use, whether you're setting up slots and boxes and stuff, or you're straight up going with permutations. Follow your heart. Yep. I'm going to keep going, though. Feel free to pause, all that jazz. Oh. How many ways can these 10 friends arrange themselves if Eliana and Steph need at least one person between them so that they don't talk? Wow, what a scenario. There are so many ways to handle this. I'm going to select one that's, I think, is particularly efficient. But if you're doing this one, and you think to yourself, well, these have to be separated, you can just have Eliana and then someone and then Steph. That's not the only option. It's at least one person between them. So that's possible. Or Eliana and then 2 people and then Steph. Or Eliana and then 3 people and then Steph. Or the other way around. Steph, then a few people, then Eliana. Or Steph, then a person, then Eliana. There's so many options. We don't need to deal with all that. That is a pain. Instead, let's check out the total number of options. Because we found that to be 10 factorial. Wasn't there 0 there? I think so. But how many of those seating arrangements do have Eliana and Steph next to each other? That's going to be a case like this one above, where we can stick Eliana and Steph in their box, and then we have boxes for everyone else. 5, 6, 7, 8, 9, 10 people. But if there's 10 boxes, this is box 1, 2, 3, 4, 5, 6, 7, 8. There are 9 boxes. So then there's 9 factorial ways to arrange the boxes, but 2 factorial ways to position Eliana and Steph within their box. And in that case, there are that many ways to play it. This is how many seating arrangements there are total. This is the number of seating arrangements where there is no one between Eliana and Steph. The difference then would be what we're after. That's what I'm getting there. Oh, there's going to be boxes all over the place here. Oh, these are good examples. Good job, whoever made these notes. Thank you. I made them myself. So Julianne and Tejal must have Robin immediately next to them. Well, if they both have Robin next to them, then Robin must be between them. Let's make them a box. Robin has to be in the middle. And this is going to be Juliana or Tejal. This is going to be Juliana or Tejal. That's 3 people. Here's a 4th person, a 5th person, a 6th person, a 7th person, an 8th person, a 9th person, a 10th person. How many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 boxes. There are 8 factorial ways to arrange those boxes. But within this box, there are 2 factorial ways. Or you could just say 2 ways. Either Juliana's first or Tejal's first. Either one works. And you'll get a value out of this. This last one is a doozy. Full disclosure, you're probably never going to see this on a provincial exam because it's such a doozy. The above one? For sure. That's fair. This is fair. This is fair. That's, oh yeah, these are all fair. This one, gracious. How do we handle it? So Jimmy and Noelle are sitting together. Robin and Tejal are sitting together. But those 2 pairs are not sitting next to each other. Okay. Now our way of treating this is going to be kind of like example E here, where Eliana and Steph needed at least one person between them. We're going to figure out the total seating arrangements that help us with this scenario and the total where those 2 groups are together so that the difference between can tell us how many options actually apply here. Thing is, we're not just going to take 10 factorial as our total seating arrangements because we're not after just any seating arrangement. We want seating arrangements that have Jimmy and Noelle together, and we want seating arrangements that have Robin and Tejal together. That's what we need. So Let's set it out. Jimmy and Noel get a box. Robin and Tejal, they get a box. This is our Jimmy Noel box. This is our Robin Tejal box. 4 people. Here's our 5th person, our 6th person, our 7th person, our 8th person, our 9th person, 10th person. How many boxes do we have? That's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 factorial ways to arrange the boxes. There are 2 factorial ways to decide what order Jimmy and Noel are sitting in. And there are 2 factorial ways to decide what order Robin and Tejal are sitting in. All in all, that gives you a number. I just want to double check my number because who knows what I get half the time. Okay, that seems to check out. So that's the total number of ways where Jimmy and Noel sit together, Robin and Tejal sit together. But we want to ensure that there's a gap between. So let's say, what if there is not a gap between those pairs? Now be careful here. We're not sticking all 4 of them in one box because we can't have like Jimmy and Noel and Robin and Tejal like that because then the Jimmy Noel pair is not sitting together. You still need, oop, it's a tiny box. You still need Jimmy and Noel together. And you still need Robin and Tejal together. But that will be treated as its own entity. And then we still have everyone else. We have 1, 2, 3, 4, 5, 6, 7. 7 factorial arrangements of those large boxes. But within there, we have 1, 2 boxes. Oh, you're right. We should color code this. Good call. 1, 2. So there are 2 boxes inside that enormous box. There are 2 factorial ways to arrange those. And then there's 2 people in each box. So there's 2 factorial ways to arrange Jimmy and Noel within their box. There is 2 factorial ways to arrange Robin and Tejal within their box. And when you calculate this, you get a number like that. This is how many options have each of those pairs sitting with the person you want to sit with. This is how many have those 2 pairs actually being right next to each other. What we want is the difference between the 2. So almost 121,000 ways for everyone to seat themselves where Jimmy and Noel sit together and Robin and Tejal sit together, but those 2 pairs not next to each other. Whoa, what an example. You know what? The greatest chaser for this would be some practice work. So there it is at the bottom. Do all of this. It will not all be like this last example, because again, that was a doozy. Gracious, chillax, man. But try it out, and as per usual, please ask me all of the questions. Any difficulty you encounter, just make sure you let me know, and I'll help work with you through it. Because this isn't necessarily the easiest stuff to get. It's very different from everything we've done before. I've mentioned that. So let me know if you're having any difficulty, and that would be super duper. Okay, see you in the future. Bye!